Listen to a talk by Alhussein Fawzi. He's going to speak, he's from DeepMind, and he's going to speak about their new work that appeared recently in Nature on machine learning for computing tensor rank.
Thank you very much, and thanks a lot for the invitation. Today's talk is going to be maybe a bit different from the other talks in the workshop, in the sense that I'll be focusing a lot on the computational aspects of computing the tensor rank, and in particular trying to see whether machine learning can help in that problem. So the machine learning techniques we will be using will be inspired from applications such as solving games like Go and chess, and then trying to adapt that to problems like tensor rank. We'll be specifically focusing on the application of finding new matrix multiplication algorithms. Okay, so I guess we're all aware of the fact that machine learning has revolutionized many fields, starting from computer vision, where image classification is now, like the performance of image classification is now very, very good, like describing images, generating images, but also like things in natural language processing, like machine translation, speech recognition, and as I said, like playing complex games like the game of Go and chess and even StarCraft. And even like a few years ago, machine learning has helped a lot in scientific discoveries, like for example, in protein folding, where we now have a machine learning system that is able to take as input amino acids and then output the 3D structure of the protein. This is a fundamental problem really in biology, and that's like very exciting to see. Today, I'll be focusing on a different domain, which is that of algorithmic discovery. Can we use machine learning to essentially like find new algorithms, essentially? So the project started with this very simple question: can we use machine learning to discover new, provably correct, efficient algorithms for impactful problems? So there are three keywords here, like provably correct, meaning that we want to find algorithms that work all the time, not just for a test distribution, for example. We really want like certificates of correctness for this to work everywhere. We're looking for efficient algorithms, and we want to focus on impactful problems, like what we call root node problems, in the sense of like if we find algorithms for these root node problems, then this can have like huge implications for other problems that depend on that. So if we're successful in doing that, in like finding a new algorithm with machine learning, that can be really transformational, because we can then use these algorithms in many applications that we use every day. And that can be really like impactful. We think that machine learning can really like be thorough in terms of like searching very large search spaces and like potentially like go beyond sometimes the intuition of humans, or at least assist humans in their intuition and work with them on the algorithmic design. Now, obviously, like there's a lot of challenges associated to this. So, as I said, we're looking to find algorithms that work fully on all instances, not just typical instances. And even like formulating the search space of like algorithms that are provably correct is extremely difficult. And when you're able to formulate that search space, then searching in that search space is just very difficult, because it's usually a very big search space. So, as I said, today I'll be focusing on the problem of matrix multiplication, because matrix multiplication is obviously a root node problem, one of the most fundamental computational problems that is used everywhere, in particular in training neural networks. So when you train neural networks, you actually have very, very large matrices that you want to multiply. Okay, so that's the outline of my talk. The first part, I'll be focusing on formalizing the problem of finding matrix multiplication algorithms as a machine learning problem. So this is like has two subparts really. The first one is how you go from like the problem of finding matrix multiplication algorithms to the problem of computing tensor rank, and I'm sure you're all familiar with that, like much more than I am. And the second part is really like how you can frame the problem of computing the tensor rank as a machine learning problem. Okay. Now, the second part is going to be like on how we can, like the method, essentially, how we can use existing state-of-the-art machine learning techniques, adapt them to the problem of computing tensor rank, and then I'll go through the results and then conclude on the remarks. Okay, so as I said, I'll go quickly on that. So the matrix multiplication tensor. So yeah, the operation of multiplying two n by n matrices can be represented by tensor, because the matrix multiplication is bilinear. The size of this tensor is n squared by n squared by n squared. If you want to multiply n by n tensor, if you want to multiply n by matrices. Like for multiplying 2 by 2 matrices, then the matrix multiplication tensor is of size 4 by 4 by 4, and it has 8 ones, and the other entries here are 0. And then we can find algorithms for matrix multiplication by getting low-rank decompositions, essentially, of this tensor. So if T is my tensor, my matrix multiplication tensor, then I want to write T as a sum of UQ times VQ times WQ, where these are, I call them factors. And over here denotes the rank of this, or like the upper bound on the rank of this tensor. Okay, so once I have this decomposition, then I can construct an algorithm to multiply any matrices A and B as follows. And then the rank R is the quantity that controls the asymptotic complexity of this algorithm. And then the very nice thing, obviously, is that you can recurse with this algorithm, so you can multiply essentially matrices of arbitrary size. Okay. So Stratton's algorithm is the prototypical example here, where Stratton's algorithm was discovered in 1969, was the first algorithm to go beyond like the n-cube complexity. And what he discovered is that you can multiply 2 by 2 matrices with 7 scalar multiplications rather than 8. And yeah, this is essentially the algorithm. And when I first learned about that, I felt like there is a lot of potential for automation and for using machine learning to detect these patterns that are, I think, very hard for humans to see. So yeah, as I said, the algorithm can be applied recursively, and you get an algorithm of complexity n to the power log base 2 of 7. Okay, so now going from tensor rank decomposition to or maybe the next slide. So yeah, our goal here is to find practical algorithms by essentially finding low-rank decompositions of this matrix multiplication tensor, right? So we will not be, I will not be talking about like improving the asymptotic complexity of matrix multiplication, which is quite different and is using much more sophisticated machinery. I think there is a lot of potential for machine learning also to improve potentially upper bounds on omega, but that's something that I think is quite different. And I think the first step really is to try to see whether machine learning can help in the tensor decomposition problem itself. Okay. So the math problem is to find low-rank decompositions of the matrix multiplication tensor. How can we use machine learning for that problem? Okay, so the way we model the problem as a game, as a sequential game, is as follows. So you have the board, which is this 3-dimensional tensor that we want to decompose. And then at each step, we subtract, like the player can choose any rank 1 tensor it wants to, okay? And then we subtract that rank 1 tensor from the board, from the tensor, and then we therefore update the board, the tensor, and then we like play R times, okay? Now, the player wins if it finds at the very end a residual tensor that is exactly equal to 0, in which case it would find a decomposition of this tensor. But we don't just want to find any rank decomposition, right? We want to find the shortest path in a way, right? So that's why we give a penalty, a -1 reward at each step that the player takes. And then at the very end, if the player fails in, like we set a maximum episode length, at the very end, if the player fails in finding the 0 tensor, then we give a penalty which is equal to an upper bound of the rank of the tensor of the residual tensor. Okay, we can compute any upper bound, and then we just give that penalty. So that's how we formulate the problem of tensor decomposition as a game. Obviously, like there's like a lot of challenges associated to this game. Like what makes it different, for example, from other games. So first of all, it's a single player game. And it has like a huge action space, right? So at each step, the player can choose really any rank 1 tensor that it wants to. So that, I mean, it has actually an infinite amount of like actions. We can discretize it, but even when we discretize it, then this actually leads to a huge action space. So think of Go, for example, it has just 300 actions. This has like orders and orders of magnitude larger actions. We don't have training data. Like in Go, for example, you have like a lot of experts, games that you can learn from, at least like initially, to learn your system and start from there. Here we don't have like available like optimal tensor rank decomposition. If we have some, then that's probably not enough to train a machine learning system. We have only one tensor to decompose. We care about the matrix multiplication tensor. We don't care about other tensors. That makes it a bit hard for machine learning systems to work, because machine learning is usually about having a test distribution, not just having one data point that you care about. But that's actually quite common in many math problems where you care about just one thing. So that's kind of like a challenge, I think, to apply machine learning for these domains. But we'll talk about a few ingredients to alleviate that. And then the final difficulty is the symmetries. Unlike like many games, this has like a lot of symmetries. Like, for example, if you permute two slices of the tensor, then you have exactly the same rank. You have a tensor rank decomposition. You can permute any order. You can see them in any order. It's equally like a tensor rank decomposition. Yeah.
So you see the non-discreteness of the problem not as a difficulty. So like there's like precision issues, right? You want to hit it exactly.
I want to get it exactly.
How
yes.
do you deal with that? Or?
So I'm going to discretize.
Is it a difficulty or not?
Yes, it's a big difficulty, and I think that's why we discretize the action space. So we're going to say that we will take factors that live, for example, in 0, -1, 1, for example. Okay, so as I said, the action space for this kind of games is way larger than Go. So this is comparing the different games in terms of like the episode length and then the action space. So like the 2x2 tensor, like the 4x4x4 tensor corresponding to 2x2 matrix multiplication has like an action space which is 10 to the 8 if we discretize it to have entries, like the factors having entries in -2 to 2, for example. Compare this to Go, which has like an action space of 362. So it's a 19 by 19 board. So it's like roughly 361, I think, +1. Yeah, and as you go, like as you consider like larger and larger tensors, you can see that the action space gets bigger and bigger. So the difficulty here is really trying to choose this needle and haystack at each step, right? So we start with this tensor, and then we want to choose the best action, and then like starting again, like doing a tree search, starting from that state, we want to select the best action again, and so on and so forth. So this animation here is shown for Go, where like all the actions, these 362 actions are shown at each step, and you do this tree search, and you select the best action at each step. But imagine that for like tensor rank decomposition and other math problems, you have like way more of these actions to select at each step. Okay. So the machine learning system we use in order to tackle this problem of tensor rank decomposition is built on a system called AlphaZero. So AlphaZero was this system that was very successful in playing Go and chess. So we're going to build on that and then like bring modifications to that in order to adapt to our problem. Okay. So let me first describe a bit what AlphaZero is about. So AlphaZero has essentially like two components, okay? So actors and learner, okay? Now the actors, you can think of them as like different computers, each one of them playing a game, okay? So like, say for example, this tensor decomposition game or the game of chess or Go and so on, okay? So each one of them is going to, at each step, open up all this tree and then like select the best action according to some metrics, and then like finish the game, okay? Now in the beginning of the training procedure, what happens is that you select actions randomly. So the games that you're going to play are going to be completely random. So for the game of tensor rank, the decompositions you're going to get are completely rubbish. Like they're going to be like very bad. But that's fine. Like through learning, we will see how things will improve. Okay, so you're going to generate, like you have all these computers, and then each one of them playing a different game. And then you're going to collect all these games, right? And then you're going to send them to the learner. Okay, the learner is where the neural network will start to understand the games that have been played. So the learner is going to take all this data that has been generated by the actors and then essentially try to imitate what the games that have been played by the actors. Okay, so you're going to take like all the moves that have been played, and then you're going to try to learn in your network to predict two things. The first one is called the policy. Okay, you're going to try to predict what is going to be the next move. Okay, what is the next move that has been in the data set that has been sent to me? Okay, and then the second one is called the value. The value is just an estimate of the rank of the current position where I am. Okay, like you can think of it as the expected future reward, right? That's the estimate of the rank of the tensor I'm going to deal with. Okay, so it's going like the neural network is going to take as input a tensor, and then the goal is to output two things: what is going to be my next action, and what is the value of this tensor? What is the estimated rank of this tensor? Okay, now I'm going to like once I send these games to the learner, I'm going to like train it for a little bit, just like one step or so, and then I'm going to send back the neural network to the actors. Okay. Now, the games that will be played by the actors now are going to be a bit better than random in the sense that I'm going to use the neural network to initialize my search somehow, and then I want to do some sort of like random exploration on top of that in order to improve just a little bit over the baseline that the neural network gives me. Okay, so I'm going to guide my search. This is called a Monte Carlo tree search based on these values of the policy and the value, but then hopefully do a bit better. And then I'm going to send again the games that are a bit better than random. And then like through this self-reinforcing loop, hopefully I'll get a neural network that is good, and then like tensor rank decompositions that are getting better and better. Okay, so that's what AlphaZero is all about. And this has been like shown to be extremely powerful in games like Go, chess, shogi. But it's really a general reinforcement learning algorithm that can be used for any problem, really. Okay, so as I said, we're going to build on that, and we're going to bring some modifications in order to take into account the challenges that I just described. Okay, so in particular, I'll go through like 4 ingredients that will try to alleviate the problems that I talked about before, which are like synthetic demonstrations. We want to diversify the target. We will train a generalist agent, and we will train a deep and tailored, like we will consider deep and tailored architectures. So that's 4 ingredients that will be on top of the AlphaZero system that I just described, and will hopefully like allow us to really tackle this tensor rank decomposition problems beyond, like, despite the difficulties. So the first ingredient. So as I said, if we want to train machine learning models, we need a lot of data, but we don't have a lot of data for math problems in general, and in particular for tensor rank decomposition. So what do? So instead, we rely on synthetic data. So tensor rank problem has this nice property that I mean, yeah, it's very difficult to go from tensor to decomposition, but if you have a decomposition, then you can construct the tensor really well, right? So that's quite obvious. So instead, what you can do is you can consider like a random decomposition, and then you can construct a tensor from it. So then you can have like pairs of like tensor and decomposition, and then you can feed that to your neural network so that it kind of like learns that mapping, right? So obviously, the decompositions that we're generating in that way are not necessarily optimal, but that's fine. It will at least learn something, and then especially in the beginning of learning, it will understand what tensor rank decomposition is, and hopefully get better by seeing the other kind of like gains that it sees from the actors. Okay, so what's also nice is that you can incorporate symmetries of your problem in the synthetic data. Let's say, for example, that you care about I don't know, like cyclic decompositions or something like that. You want to find decompositions, like if you have a factor UVW, then you also have a VWU and WUV and so on. Then you can generate a data set like that, and therefore the neural network will actually output always decompositions that are cyclic. Yeah, so as I said, like the training of the network will have 2 sources. The first source are the actors, as I described before, And then the second source are these synthetic data that we just described. Yeah?
Catch it. Do you feed the synthetic data to the actors or to the learner?
To the learner. Yeah. So here, like I will go again through the full picture after I described the 4 ingredients, but essentially, like the learner, this is the learner part, and this is the actor. Okay. Now, the learner has 2 types of inputs. The gains that come from the actor, but also we consider like these synthetic demonstrations. Okay. So one of the issues, obviously, of considering synthetic data is that what we care about, the tensor that we actually care about, is very different from the random generated data that we consider. So that's a problem, but the idea of like having this mix of the 2 is that the actors generate like this data that is like belonging to the distribution that you care about, and the other is just helping you, especially in the beginning, to kind of like get started in this problem of tensor rank decomposition. Okay, the second ingredient is essentially related to this problem I described before of that we have just one tensor that we care about, this matrix multiplication tensor. So and this is a very atypical scenario in machine learning. In general, we care about like a performance over a test data, like a lot of data points rather than just one. So what do we do to tackle that? Well, actually, there is a very simple solution to this. You can take the matrix multiplication tensor and then you can change the basis, right? So in this way, you can generate like so many tensors that are equivalent, mathematically are equivalent to this tensor that you care about. But for the neural network, it actually doesn't know that it's equivalent, so it treats it all in a different way. So whenever you find a good low-rank decomposition of the tensor in a changed basis, then you can go back, obviously, and then you can essentially like propagate this information quite easily. So hopefully, by doing this random change of basis, what happens is that the matrix multiplication tensor, when you do this change of basis, it kind of like gets closer to this distribution on which you train them on synthetic data, and it kind of like helps it to generalize. The third ingredient I want to focus on is to train a generalist agent rather than several experts. So one approach would just be to train a system like this AlphaTensor system on a particular tensor size, right? But that's actually not a good idea. It's much better to train just one machine learning system on all the tensors that you care about. Let's say that you care about matrix multiplication tensors from size 2 to size 10 or something. Then you train on all of them together. And then what you'll see is that there is positive transfer happening across the different targets. So the idea is that it will kind of discover techniques for small tensors and then transfer these to larger ones. And it's been actually quite surprising how much transfer happens between targets that we thought didn't have any relation between them. So obviously you'd have like transfer between 2 by 2 to like 4 by 4 because like there is this natural mathematical relation. But then like we saw transfer like happening between things we didn't know that have any relation, like 2, 3, 4, and I don't know, like 3, 4, 4, 4, 4, 4, and so on. So whenever you remove one of the targets, then it kind of like doesn't know how to handle the other one anymore. So it's very important to consider all these problems at once. Even more than that, it's actually quite important to consider different fields. Let's say that you want to decompose tensors in a certain field or in different fields. Then if you treat the problem separately, you'll less likely get better, like you'll not be as performant as if you treat the problem all at once. Because there is transfer that might happen between finite fields and then like other fields that you consider. So, for example, we tried to decompose tensors in GF2, and at the same time in like by considering integers like -2 to 2, and then like there is transfer that happens between these two. Whenever it discovers like a tensor rank decomposition for a finite field, then it might transfer somehow to. So we don't know exactly what's happening. That's the thing. We don't know what it is exactly it's learning. But as long as we get a tensor rank decomposition, then we can easily check it. That's the idea. Yeah. So it's all beneficial, I think, to train this generalist agent because we get better performance through transfer. as I just said, but it's also much more efficient. Like if we had to train one neural network for each metric size, then I think that would be like very computationally heavy. Yeah.
So you mentioned you use different formats for matrix multiplication, but have you also done like multiplication in algebras? I mean, thrown that in as a diversifying?
No, I didn't try that. No. Okay. Now the fourth ingredient and the last ingredient I want to go through is the architecture of the machine learning system, of the neural network itself. So sometimes there is this preconceived idea that we can just consider like dumb but very deep neural networks, and then it will just work out of the box. But this is definitely not the case. Like one has to actually like throw a lot of expertise and potentially some, intelligence in the machine learning system so that it starts really to work. Okay, so that's like we should really go beyond that, these shallow fully connected layers, or even like deep fully connected layers. So one thing that has been introduced recently in the machine learning community and that works really well is the concept of attention and transformers. And this has been like very useful in machine translation and natural language processing at large, but recently even like in, for example, the protein folding project that I described you before, and also in this one, like attention has been really fundamental. So in a very superficial maybe explanation of attention is essentially that you want to build relationships between entities of your data. Okay, so suppose, for example, that you have a machine translation task where you want to translate from English to French. One way to do it would just be to do it word by word, right? But that would be really bad. So instead, what you do is that you try to learn to attend between different matrices. Between different tokens, between different words. Okay, so you try to learn the relationship between this word and so on and so forth. So the idea is that when you learn to attend, like there might be very long-term relationships that you're going to learn, and it's going to be much better than treating things one word at a time. Okay, and that's how modern machine translations is based on. It's based on this concept of attention. So this is not specific, as I said, to natural language processing, because you could replace these words by something else. You could replace them with the matrices. You can replace them with vectors, with tensors, and so on. And then you can learn to attend between different entries, between different entities you have in your data. And we'll see in a bit like how we can use that. But first, before we go in that direction, let me like just remind you of how the machine learning architecture looks like. So we have this tensor that we feed in as input in the learner, and then we have a common part which is called the torso, and then we want to predict two things. Remember, you want to predict the policy, which is this rank 1 tensor, or like the UVW, and then you want to predict the value, and the value corresponds really to the estimate of the rank of the tensor that you feed in as input. Okay. Now, I will not go in detail on the policy and the value because that's pretty standard neural networks. Now, the torso is where we can have this attention mechanisms a bit. So what you do in the torso is the following. So you have this tensor, so this three-dimensional tensor, and then you can project this three-dimensional tensor into 3 grids, essentially. So the problem with the tensor is that it's quite high dimensional. So it's quite difficult to manipulate and do attention on it. So instead, you're going to project on 3 different views of the tensor. So kind of like you're going to take the tensor, you're going to apply a linear layer to get some grid, and then you're going to transpose it and then apply a linear layer. You're going to get a second grid and then transpose it again to get a third grid. So the idea is to kind of get different information from different views of the tensor. Obviously, you're losing some information, but that was good enough for learning. And the idea is to try to attend between different entries you have in your grids. So in particular here, what we consider is attention between entries that you have in this grid here, like these entries here and those entries here. So what you want to do here is that you want to attend between the different entries you have in one slice. so that you say essentially to the machine learning system that these are more related to each other than entries you have on different slices, essentially. So you're kind of like building some inductive bias about the problem in the machine learning system, kind of like by giving it some information about the what slices mean in tensors. You're also building some invariance in the sense that attention is attention on a set, so it's order invariant. And so, like if you're permuting slices, then you're going to get exactly the same result. You're going to get the same like output of the neural network. Yeah. So the overall system, after like I described these 4 ingredients, is as follows. So let me go through that. So you have, as I said before, you have actors and you have a learner. Right? So what you do is that you start with this tensor that you want to decompose, right? And then you don't consider that right away, but you do some random change of basis, okay? And you get this blue tensor, this red tensor here. And then you're going to do this Monte Carlo tree search I described before, okay? And then you're going to get the first action, right? And then you're going to update your tensor. You're going to apply this Monte Carlo tree search based on the guided by the neural network, okay? And then you're going to get the second factor and so on and so forth till you finish your game. After you finish your game, you're going to send this game to the learner, and the learner is going to put that in some data set, as well as the pre-generated synthetic demonstrations. You're going to sample from this union of data sets. And then you're going to try to predict the policy and the value using the architecture that I just described. So what is going to be my next step and what is the estimated rank, okay? Yeah?
Right how to decide that the game of the actors is finished.
Yeah, so we set a maximum episode length. Let's say, for example, that, I don't know, like for the case of 4x4x4, for example, you give it till 8 steps, okay? After 8 steps, you kind of like say, okay, like if you didn't find a 0 tensor at that point, just stop. And then just stop and you give it a penalty, which is just an upper bound on the rank of the residual tensor. Because, I mean, it's not very useful to kind of like continue indefinitely, because anyway, it's not going to be a good episode. Any questions on the, yeah?
When you say next step, the value and the policy of the next step,
yeah,
I got a complete game, well, several complete games. So stepping what, like, we're not in the middle of a game. So what do you mean? Value of what?
Yeah.
Next steps.
So when we send the full game, you can think of like in this example that I just gave before, you have like 8 steps, right? So when we send the full game, but then you can think of it as like 8 data points, right? Yeah, exactly.
In the middle and check yourself if you do it right.
Yeah, so you can think of like this full game as 8 data points, where at each step you have an input tensor, and then what is the value and what is the policy, right? And then you can train the neural network on these 8 data points, right? You can sample any of these and train.
Consider the played game as the ground truth.
Yes. Oh yeah. So I mean, because you finished your game, right? So you know exactly what is good. You can backtrack the value, right?
Okay.
Yeah. Yeah.
Just a quick question for the linear layer in the previous slide.
Yeah.
Is it just a linear transformation of the whole tensor itself?
Yeah.
Matrix?
Yeah, exactly. Yeah. Yeah. So, I mean, we call it sometimes in machine learning a 1D convolution. So you kind of like, you have a filter here and you apply the same linear weights on each of the.
It's just like linear application of the slices.
Yes, exactly. Exactly. Yeah. Exactly.
You keep that fit. Do you always do the same projection? No.
No, that's learned.
Yeah.
This is like, yeah. Yep.
Actually, I have a follow-up question because you said you train on tensors of different sizes.
Yes.
So how do you handle that?
Yeah, so we pad with zeros. So let's say we want to do one 4x4x4, but we pad with till 25 by 25. Okay, so let me go through the results. So as I said, we train on everything at the same time. So this is the set of tensors that we train on. So from 2 to 2 to 5 by 5 by 5, meaning that you like the problem like at each row is like to multiply n by m times n by p matrices. And then like we have a tabulation of the best rank for each of these rows, right? And then, as I said, you can consider like working in different fields. So this modular field is like GF2, but really like the results we get are for any field with characteristic 2. And then the standard one is essentially like considering like the normal, the integers, where we restrict the factors to be between -2 and 2. So as I said, in the beginning, it just does really bad. But then through training, it gets better and better. So for example, in the beginning, the 2 to 2, it just gets to 8, like the normal, the trivial matrix multiplication algorithm. But then at some point, you rediscover Strassen's algorithm. And then like bit by bit, you get better and better on the larger tensors. And then at some point, you get better than the non-results. Yep, and so all these algorithms are outperforming the existing non algorithms in terms of the rank. So one particular interesting result is that we were able to get beyond the algorithm, like the Strassen square algorithm of applying it twice in fields of characteristic 2, where the best result was just 49, applying 7 times 7, but we were able to get to 47 with this approach, and which leads to an algorithm of like n to the power 2.77 on a field of characteristic 2. So yeah, as I said, we train all these things, like everything in this table is trained just at the same time, like modular and standard. Okay. Okay, so this is an example. This is actually the algorithm we get for 4x4 matrix multiplication for like GF2. So yeah, it just shows how like maybe difficult it looks like to get, I think, like a construction by a human. So I think it's really easy to check, but it's quite difficult, I think, especially I think in finite fields like GF2, where it's I think even more non-intuitive. Yeah. Yeah, I mean it's really hard. Like how do you? It's really hard to ask it to. So the machine is like doing what the machine is supposed to do, but so what is interesting, for example, is that we. I mean, hopefully yes, because so we open source the data set of all the decompositions that it found. So for example, even in the standard case, so we were not able to find 47 in the standard case, but we got 49, and all these 49s, or like most of the 49s that it found, are not equivalent to Strassen squares algorithm. So not equivalent in a sense where you cannot go from one to the other using simple transformations. So it went really beyond what like the application of Strassen like twice does. So we open source this, but I don't think we're really looking forward to collaborate with mathematicians to better understand what these algorithms, what the neural network is actually doing. Yeah,
it's interesting because when Strassen found, I mean, the story goes that when Strassen found the rank 7 decomposition, he did it first over F2.
Oh, interesting.
And then he found the right sign pattern somehow.
Okay.
To make it work over other fields. But of course, your decomposition is so big that like finding the right sign pattern, if it exists.
We tried to apply some like SAT solvers to try to, you know, like say, okay, like we have this decomposition.
Yeah.
Yeah, we have this decomposition, so let's try to actually just solve for the signs.
Yeah.
To see whether we can like, but unfortunately, it was not successful. Sorry?
You only copy it.
Just like how many of this decomposition are 48?
47. We can find a lot of. We can find thousands of them. Yeah, that are not equivalent. So we have a database of like thousands of decompositions like this that are all non-equivalent in some sense. But we tried all of them, like in terms of like.
Like the dimension of this solution.
You mean like the manifold dimension or something like that? Yeah, we didn't really try that. Yeah. Okay. Okay, 20 minutes. Yeah, so as I said, like the procedure really finds thousands of inequivalent decomposition for each target. So we open source that data set of factorizations, and I think it can help us better understand the space of matrix multiplication algorithms. So we're looking forward to really trying to leverage that. And the other interesting bit of like finding diverse decompositions is that you can recombine these for like some sort of divide and conquer approach, and leveraging the diversity of the algorithms that you find, you can improve on larger tensors. Like this graph here shows the improvement in rank that we get for like larger tensors. So yeah, the x-axis shows the best rank known, and then the y-axis shows the improvement. Using this divide and conquer approach, where you combine different matrix multiplication algorithms that we found using this machine learning system. Okay. Yeah, so I mean, what we built is really not specific to matrix multiplication tensors. You can apply it really to any bilinear operation. So we tried that, and we said, okay, let's try it like a special bilinear algorithm, which is multiplying skew-symmetric matrix vector product, for example. So you can do that for different n's. So that's a n by n times n by 1 product. And then you can find all these decompositions. So that's essentially like the decompositions that the machine learning system finds. And then you can see that there is some pattern, and then you can extrapolate that pattern to get an algorithm, and then you can prove the correctness of this algorithm. So that's also something you can do with this machine learning system. And this this improves over the previous best known results in terms of the number of multiplications. Now, so what, like, I think one of the big advantages of this reinforcement learning algorithms is that the reward function can be really anything. Like, it doesn't need to be differentiable. It can be really anything that you can think of in terms of computing it. So we did actually like stretch that direction in the sense of like saying, okay, what if we try to put in the reward the actual time that this matrix multiplication takes on a specific hardware, like on a hardware accelerator, like V100, like a GPU or a TPU, for example. So it's exactly the same setting as before, but at the very end, I give it an extra reward, which is like rewarding the algorithms that are actually fast on that hardware. And the algorithms we get are actually quite a bit better than the normal matrix multiplication that is used in a library like JAX or NumPy on these accelerators. I mean, yeah, NumPy is not really on GPU, but like JAX on GPU and TPU. So so this is essentially like showing the performance improvements over like the normal matrix multiplies, where Strassen shows you the normal Strassen's algorithm, and this is what we get. So you can see that it improves quite a bit with respect to the normal algorithm, and a bit over Strassen's algorithm. And what's very interesting is that when you try to optimize the algorithm for a certain hardware, like a GPU, then you get good algorithms for GPU, but that are actually very bad on another type of accelerator, which is TPU, and vice versa. Okay, so there are some things that are quite specific to the hardware accelerators that we're considering. I mean, obviously, again, it's quite hard to interpret why is a specific algorithm better for GPU than TPU. Yeah, this is quite interesting to see. Yeah, so that's my final slide. So the starting point really of this project was to say, okay, like we were really successful in playing games like chess, Go, and so on. But what about like just trying to take this technology and like apply it to combinatorial problems and like to find new algorithms and so on. And so I hope I convinced you that machine learning can be quite useful for these problems, for these very hard combinatorial problems. There are obviously a few limitations, like the limitations of this work are specifically that we consider like a finite entry set. So like for each entry in our factors, we have to specify something like a finite set. But there might be potential for going beyond that. And there is no optimality promise, obviously. So like when you get a decomposition, you don't know whether this decomposition is optimal or no in any sense. So it doesn't give you a lower bound, right? But I think that what I'm really excited about is that these techniques are very general. So you can see that we put actually very little prior knowledge about about the problem of tensor decomposition at large. So we think that this can be applied obviously to other bilinear operations, to other notions of rank, to other search problems, and we're very excited about like pursuing these directions. It's also quite general in terms of like spaces. As I said, like we work on finite fields, but you can essentially like work in any domain where you have a multiplication table that you can just feed to the machine. And finally, as I just mentioned, in terms of objective functions, you can really consider anything like in terms of runtime memory, but also like let's say you want to solve an optimization problem in your rewards computation, you can also do that. So yeah, I think there is a lot of promise in using machine learning for these types of problems, and I'm looking forward if you have like ideas you want to discuss and so on. I'm really happy to do that. Thank you very much. Thanks.
Questions?
I have a philosophical question.
Yeah, sure.
Why did you try this with the, I mean, it's in theory, it's a very basic algorithm, like a tensor that's subtract random tensor, right?
Yeah.
And so why not to try with an algorithm that brings, that you know that at some point will bring you to the rank of your tensor?
Not sure I understand. What do you mean?
So if you have an algorithm that you know that if you have enough power of your computer, at certain point it will bring exactly to the rank of your tensor. So why don't do that rather than attempt or decreasing the.
So you mean the actors? Why do we try like several times or?
So probably I should rephrase it in a different way. So is it possible to apply such a machine learning technique to a different kind of algorithm? So an algorithm that at the end you are sure that it will bring you to the rank of your tensor.
To the real rank, you mean to the So to give you a certificate that it's it might be possible, but it's just that this approach is, as you said, very simple, and it doesn't give you any guarantees that it's really the optimal thing. But I mean, we don't have any ideas on how one can do that. But if there is a way to formulate it in some sort of like sequential game, then it might be possible. But I don't know any way to do that.
I'm surprised by these thousands of solutions that are equivalent. Are they inequivalent under the symmetries of the tensor?
Yes. So like there are a few symmetries. Like for example, obviously, like if you have a decomposition, because the matrix multiplication tensor is cyclic, you could like change the UVW to VWU and so on. And that's one. You can apply some matrices like as a matrix multiplication, like A, U, A minus 1, and so on. So this is like a group of symmetries which we took from the literature, and that Strassen has shown, or like I think a later paper, I think, has shown that it's the only algorithm under this group of symmetries. But yeah, so we consider that group of symmetries, and then like under this, it's there are like at least 14,000. I'm sure there is much more than that. It's a bit strange when you think about it, because like 4x4 matrix multiplication sounds like not you can't do much with it, but there's How
long did you work on this project and how many?
I mean, it depends. Like if you count like the paper writing and like rebuttals and all the things, it's like
till the paper is till we found the 47.
Till we find the 47. So 1 to 2 years. Like core contributors or like people just advising and so on. That's different.
In full-time equivalent.
I don't know, like maybe 4, 5. But I think
what was your computational resources?
Yeah, so in the particular example that I gave here, you're kind of like you have 1,600 actors, so 1,600 machines. And the learner is just a TPU, which is I don't know, like if we like I can give you the details, but I'm not sure like it will be very relevant.
Just to get an idea.
Yeah, so it's like you can think of it as like maybe tens of GPUs.
Okay, so you have like 1,600 actors, and they are like normal computers or GPUs.
No, these are also like, because there is, you need to evaluate. So there is like what we call inference TPUs. So they're a bit, they're not so powerful.
What? Let's get some of them.
So they're inference TPUs, so lower memory. They're lower memory than the other one, than the learner, because the learner needs to backpropagate. So that needs a lot of memory, but the other one just needs to feed forward, right? So these are called inference TPUs, and there's like 1,600 of them.
Sorry, I can ask infinitely many questions on this, but sort of like, is this possible to? So I mean, at least what I heard is that like AlphaFold, it's not possible for university to repeat this, right? To repeat the training stage. Is it possible to repeat this?
No, I don't think so. At the current stage where we are, no, I think it's beyond really university research. Yes, I think so. There might be a lot of potential for like, I mean, feeding in more prior knowledge and potentially like reducing a lot of the search space and then finding similar algorithms. But yeah, what we started with is really like very little prior knowledge and yeah, some compute.
So because in this AlphaFold, if I only had a superficial conversation with someone on this, but there apparently you can execute it, right? But you can train.
Yes.
The training thing, like we couldn't repeat.
Yes.
But we can execute it.
Yes, there is a
collapse situation here because there's not so much data to train.
Yes. Yes.
What is the bottleneck here?
So yeah, if we I mean, there is here, it's a bit different because there is a Monte Carlo tree search, and the Monte Carlo tree search is the thing that takes a long time. It's a bit like if I give you AlphaGo, you know, like you cannot really run it because you need to run so many simulations at each step, at each board game, you know, at each step of your game, you need to execute like, I don't know, like thousands or like hundreds of simulations. And that means like you need to run hundreds of times your neural network because you want to compute the value and policy, and then you take a step. And then you want to compute hundreds of times, and then you take a step and so on. Whereas AlphaFold is a bit different in the sense that it's a supervised learning problem. So you take your amino acids, you just run it on it, and then you get the output essentially. So RL is usually way more compute heavy than supervised learning, even to just at inference time.
Just follow up on the recent discussion. I've moved from table probably for the finite time. How much more kinds of is there any hope to do 100 by 100 or completely?
No, I think 100 by 100 is pretty difficult, just even to store the tensor. It's like, but probably this approach can maybe scale to maybe 10 by 10, I'd say. But I think like if we want to study like much bigger tensors, then we have to use some of the prior knowledge about like, or put some maybe extra constraints. Like for example, I think that if we were looking for a symmetric decomposition, like a UUU type of decomposition, then we could scale to much larger tensor.
The 47.
Yeah.
Does it use the 2 and -2, or does it stay in the 0, 1, -1?
I think it uses just 0, 1, -1. Yeah. So it might be that it uses 2 and -2, but in a changed basis. But when you kind of like change it back to the original thing, it's.
So did you fix that from the beginning? That set like from -2 to 2.
Yeah,
you just went with that.
Yeah. There might be better options there for sure.
I was also wondering if you could like maybe first solve modulo 2 and then modulo 4 and modulo 2, you know, kind of this lifting. Have you tried that?
No, I haven't tried.
Well, sometimes that's kind of a lift that might be even unique or into very little things, right? That's how factor polynomials over the integers. You first do it modulo 2 and then 4 and so on.
Yeah.
And then you get a factorization of that.
But I mean, the algorithms that we found are also applied to GF4 and GF8 and so on, because they work on any field of characteristic 2.
But that's kind of a different thing.
Yeah.
Another question I had was, So do you kind of like do you actually know like for random tensors of a certain size, you know, what sort of the generic rank or order rank is? So do you use that information? For example, if you have a 2 by 2 by 2 tensor, we know that the border rank is at most 2. So you could even perhaps allow different moves where instead of subtracting just a rank 1 tensor, you could subtract some core tensors of that size.
Yeah, no, we haven't used that at all. So, but that's a good point. Yeah.
The multiplication tensor.
No, because you know upper bound.
Yeah.
Would it be easy to adjust to like slice rank, for example, or all these other?
I think so. Yeah. The action space will be a bit different, but I think it's adapted to.
Yeah. For example, 4 by 4 by 4 tensor. Every tensor has border rank at both sides. So it's the major multiplication is actually not special.
Interesting. Yeah. So the short answer is no, we didn't use that at all. But there might be potential.
Yeah, I mean, you could kind of enter this as information, right? Just you take some core tensor and add it, or you could take any tensor and some bound for them.
Yeah.
So in the very beginning, you said you were looking for probably correct, efficient algorithms for impactful problems.
Yeah.
Now you have this one. What are other candidates?
I don't think we finished this. Like,
Fine, I understood. But,
yeah. That's something where
other teams, I don't know, or other examples,
yeah, I mean, hopefully in the next few months there will be other examples, but yeah, for matrix multiplication, for example, we're quite interested in trying to improve omega, the upper bound on omega, I mean. And yeah, in the like big space of algorithmic discovery, we're just in exploration mode currently, where we're trying to see which problems can be amenable to similar types of search algorithms.
I was wondering, of course, we don't know what's going on really inside the machine learning. Right?
Yeah.
But can we distill some sort of heuristic about like which rank 1 tensor to subtract? For example, I once had a strategy that I applied to a tensor and it worked very well. And what I did is I had this lower bound method, which is called Young flattenings.
Yeah.
And I would compute the Young flattening of my tensor, and then I would subtract a rank 1 tensor and see if that flattening went down. Young flattening. That was my heuristic. Okay, fine.
Yeah.
So this is some function. But can you like distill such functions like that tell you that you're going in the right direction and that other people can then use?
Yeah, I think so. Yeah, I mean, at each step we can try to use like Young flattenings or other lower bounds or even upper bounds to try to see which like what are the, for example, the nodes that have the biggest difference between like lower bound and upper bound, or some where we want to really explore more. So here we're only relying on the value function, and the value function is giving you that information somehow. Like the neural network is trying to learn that, but maybe we can help the neural network by giving it some of these.
Or in the other direction, can you distill the function?
Like take the value function that has been learned and then
make it actually write it down, or like have a.
Yeah, but I mean,
still some function out of it.
I mean, it might be possible that like this neural network is just a bunch of weights.
Yeah.
So yeah.
The function is the whole network.
Exactly. Yeah. There is some work on that, on trying to like take a neural network and then try to distill it into some easier function. But I think it hasn't been like very successful, I think, so far, because either you're losing some information in terms of like, or you're losing some power of the neural network. Or you're just not getting, I think, interpretable functions. Essentially.
In this line, so there for small tensors, you may know exactly which are the for your given tensor, which is the forbidden locus or the decomposition locus, so the place where you are sure that there's no point appearing in the decomposition that way around. So this could be something that you may feed into. How
do you compute that locus?
Sorry?
How do you compute that locus?
I mean, there's not a global strategy. For small tensors, there's there's a classification in being by the compositional locus and the forbidden locus.
I mean,
it's mathematicians.
Yeah.
There's not a global strategy. Right? There's not a theorem that tells you this is always the forbidden locus, but in some cases you know exactly what they are.
I see. Yeah. And by small, what do you mean? Like what kind?
Like rank 3, rank up to
But I mean, this is usually like neural network is pretty good at these range of sizes and ranks. It's really like when it's like quite big tensors, and especially in the beginning, like the choices it has to make at the beginning are the ones that are kind of crucial. But when it's near the end, it nails it down really. So
thanks.
Thank you.